Good afternoon, everyone, or at least afternoon in Washington, D.C. About 25% of our audience today is international. It's a beautiful day here. I'm going to say hello specifically to a class we have tuning in from Colorado University at Boulder, and also to Susan Ensel and her class at Hood University in Pennsylvania. Let me introduce our speakers. David Finster is a professor of inorganic chemistry at Wittenberg University in Springfield, Ohio, where he is also the University Chemical Hygiene Officer. David has a BS degree from Bowling Green University and a PhD from the University of Virginia under Russell Grimes. He was a postdoc with Chris Reed at the University of Southern California. David has carried out research in boron chemistry, electrochemistry, and the synthesis of inorganic direnium compounds. He has also published about the application of student development theory to chemistry teaching. David has written a textbook on laboratory safety for chemistry students that's published by Wiley InterScience, and he's also a member of the ACS Committee on Chemical Safety. Jeffrey Whitford is the Director of Global Citizenship at Sigma-Aldrich Chemicals. Jeffrey earned a bachelor's degree in journalism from the University of Missouri-Columbia and a master's degree in business administration at Washington University in St. Louis. Jeffrey's responsible for developing and implementing strategic programs to enhance Sigma-Aldrich's position as a global leader in greener chemistry and environmental sustainability and social responsibility. And he also works to integrate sustainable development concepts into the strategic plans for each of Sigma-Aldrich's business units. And so now I turn the floor over to David as our first presenter this afternoon.
I'm happy to be here to talk about connections between green and safe chemistry, and we'll get right to the task here. As it's occurred to me over the past handful of years, many of us have an interest in green chemistry, kind of what I call the EPA side of chemistry, protecting the environment. That seems like a laudable goal for chemists, that's for sure. And then I've also been interested in chemical safety, and I kind of think of that as the OSHA side of chemistry. So it's occurred to me to think about the connections between these two. What I want to do today then is to do a quick review of the 12 principles of green chemistry and how they connect to safety or not. I assume most listeners probably are vaguely familiar with these 12 principles here, so I'll go through this pretty quickly. And then later on we'll start to compare green chemistry and safe chemistry, specifically inherently safe design. Some of this should be obvious, right? We'll go in order pretty much here, except we'll start with number 12. Borders on the obvious. Green chemistry would have us use safer chemicals in lots of facilities to avoid the kind of accidents that we see on the screen here. But the implied goal in green chemistry is really to protect the environment using safer chemicals, but it borders on the obvious then that if we have safer chemicals that are going to protect the environment to avoid these kinds of catastrophes, that will also necessarily be a lot safer for the employees. So we don't get high credit for picking number 12 as relating to safe chemistry in the laboratory. So let's just dance through the other 11 here. Number 1 is better to prevent waste than to clean up waste after it's been created. And again, if the waste presents some hazard, the less you have of it, not only is it better for the environment, better for employees. Atom economy is an idea we've come to know about in green chemistry. And of course, here's the idea that you would like to take all of the atoms in your two reactants and put them into your single product, preferably, and have as few atoms left over as byproduct as possible. And you know, we all know you can have a reaction of very, very high yield, but still very, very poor atom economy. The Wittig reaction shown on the screen is one example of that. But the point for safety then would be if I don't produce these byproducts, or if they have hazardous chemicals and I can avoid producing them, then that's going to be safer for the people that are doing the chemistry. Less hazardous chemical synthesis, right? So we ought to be designing chemicals and substances that present little or no human toxicity for the environment. And of course, if it's safer for the environment, it's safer for employees. Designing safer chemicals, again, this almost seems redundant from our point of view now, that if we have minimizing products that have a lower toxicity is going to be safer for employees as well and laboratory workers because less hazard for them. We all know about the idea of using safer solvents or even getting rid of solvents so that things are safer for the environment post-reaction and during the reaction, but obviously getting rid of hazardous solvents and flammable solvents will be safer for employees as well. So far so good, it seems. Energy requirement, clearly, if we can design for energy efficiency in a reaction, we'll be working at more ambient temperatures and pressures. Those will be inherently safer for employees too. Reducing derivatives along the way, minimizing the number of steps we need in some synthesis, right? If we simply have fewer reagents and fewer intermediates that need to be processed, that's going to be safer for employees. Using catalysts, again, that's probably going to require milder reaction conditions. We'd need to worry about the toxicity of the catalyst, but in general here, if we have milder conditions for a reaction, that would be safer for employees as well. The real-time analysis for pollution prevention will help keep employees safe because if we're able to monitor reactions rather than just hoping that they're staying within design parameters, that will be safer for employees too. So pretty much a strong theme developing here. As I've been thinking about these, though, when I got to number 7 about use of renewable feedstocks, it wasn't clear to me that whether a feedstock is a raw material or some other source doesn't necessarily make it inherently safer or less safe. So I kind of give that a lower ranking with regard to employee safety. If you want to disagree with this later on, that's what we have question and answer for, I guess. And the same for designing for degradation. That makes perfect sense for green chemistry, but that's a really down the road sort of thing if you're working in the lab or in a factory, so you wouldn't worry as much about this factor. My count is that we get about 10 of the 12 principles are really directly related to laboratory safety. Is there any instance where making the lab safer for workers in an OSHA sense compromises the green chemistry principle? So if we're trying to be safer, we're actually doing some damage to the environment. The only thing I could think of when I thought about this is when we're exhausting to the environment to keep our laboratory safe. But I think most of us, certainly in a research laboratory, realize that we're exhausting a small amount of dangerous fumes or gases to a very, very large atmosphere. In a plant situation, that could be a little bit differently, so we'd have to be somewhat mindful of that. I'll be merciful and not read through this in any detail, but just showing some of the Presidential Green Chemistry Awards. You can see the blue items in the middle column there are the features that make something greener, and then I just highlighted the safety aspect of that same process. And as you can see, one of the keywords is, we eliminate and reduce hazardous materials along the way, and that's certainly going to always make the laboratory and factory a safer place. The process of inherently safer design, this is more of a chemical engineering way to view process safety. Again, I won't read through all this, but you can see how I've lined up most of the 12 principles on the right-hand side of the screen and how they connect to the process steps that chemical engineers would like to have in their materials in factories and large synthesis areas. The way we started to think about this is this diagram that OSHA produced a couple of years ago, and has been I've been assisted by Shelley Bradley, as you see at the bottom here, and Tom Goodwin at Hendrix College to kind of put together this OSHA diagram. We modified it just a little bit. It's the colors in the triangle are all the same there, but when you think about the different options, we use all of these. All of us use all of these in different situations, but at the top of the triangle, if you can eliminate the hazard entirely, then you really eliminate the need for all the other practices that we ordinarily have to use. So we use PPE and hoods and training because we know we're going to be encountering some hazardous substances, but if we could eliminate those, which of course is one of the ultimate goals of green chemistry, then we're going to be in a lot better shape. So just a couple more ideas. This is a list of things people can do in labs, right, to make their lab greener from the Green Chemistry Institute at Toronto. And I've kind of supplied the arrows on the left there that said, look at all these things that if you just make it greener, these will inherently be safer steps too. So I think I kind of keep driving home the same point over and over again here. So my conclusion is that if you're doing green chemistry, you're doing safe chemistry, and probably we could talk about how often when you're doing safe chemistry driven by OSHA concerns, you end up doing some aspects of green chemistry. So I like to really think about these kind of in the same breath at times, and when I'm teaching this to my students, I try to make the strong connections between these two. So that's it for me. Let me pass this over to Jeffrey now, who's going to talk about his perspective from Sigma-Aldrich and the strategies that they're taking there.
Perfect. Thank you, David. So now we're going to take a moment and talk about transitioning from the building blocks and moving into how we are implementing these things at Sigma-Aldrich and how green chemistry is actually applied. You heard that I worked in global citizenship, and you may think, what's the connection between global citizenship and green chemistry? And really, that link is how we maximize the benefit or good that we do as a company, which is we look at this and say is the implementation of reducing hazard, risk, environmental harm by implementing green chemistry and helping to spread that process to our customers globally and then implement it ourselves as we manufacture products. So I think that idea about information was something that we took to heart, and when we talked to our customers, it was something that they identified to us that they needed help with. What we did was we took those things that you heard from David, the 12 principles of green chemistry, and really used that as the framework for us to build our green chemistry roadmap out of, and really taking this holistic approach to the entire value chain around green chemistry. So the products that we manufacture and looking at how we could re-engineer those products, expanding the portfolio of products that we offer, increasing the information that we give our customers through marketing and the information available on Sigma-Aldrich.com, and then taking you through the transport use phase that you use in your labs, and then talking also about education advocacy and how do we begin to change the dynamic of education earlier on so that more people are learning about green chemistry earlier in their education cycle. So on the information front, you'll see on the left-hand side of your screen a globe with an arrow around it. This symbol now is on Sigma-Aldrich.com next to any product that we've identified as a greener product. One of the key things about this that we'll talk about later is the information required to get that symbol. So it's not just arbitrarily applied. There are characteristics that must be presented for it to be considered a greener product. And then we've broken that down into three categories. And I'm going to talk about two of those three categories today, the re-engineered category as well as the 12 principles aligned category. The third category, the enabling technologies that you see on the bottom, are really the mix of our specialty enzymes and material science products that we utilize for alternative energy research, biofuels, photovoltaics, etc. So one of the things that most people don't know about Sigma-Aldrich is that we're not just a distributor. We're also a manufacturer of these chemicals, and we've got scientists throughout the world. We actually have 9 centers of green chemistry excellence spread around the world. We've got about 40 scientists who work on a time basis on green chemistry and have actively re-engineered more than 30 products, and we'll talk more about what that actually looks like. The quantification of information really became one of the key things that we focused in on. So we had done all of this great work about reducing the environmental impact of the products, but we didn't have a good way to communicate that. So we actually introduced a system this past year called Dozen, and it is a quantitative green chemistry evaluator, and we're going to get into some of the examples of what this actually means and what it does. So when people asked us, well, why is this greener? We had to create a good way to communicate that. And so now using Dozen, we're able to actually quantify the improvements that we make from product changes. So beta amylase, which you see on the screen, is an enzyme extracted from sweet potatoes. And we had 2 enterprising scientists who had a passion for craft brewing at home. So nothing like being able to take an outside passion and bring it inside to the lab. But they found a reference from a 1950s text that they were able to introduce into their process in the manufacture of beta amylase. And they were able to significantly affect the manufacturing process. We were able to use about a third of the amount of sweet potatoes that we typically use to manufacture this process. The original amount that we used the first of this process was 6,000 pounds of sweet potatoes. So we took that down significantly. We actually were able to eliminate all organic solvent usage. So for the manufacture of this, that was about 1,900 gallons of acetone no longer used in the manufacture of this product. And then we're able to eliminate the need for heat and elevated temperature and pressure to make the reaction occur. And so what you see are these percentage improvements. So we put all of this information that comes from the manufacturing process as well as GHS information into the system. Each of their 12 principles has an algorithm. Out comes a score that we can compare to. And here you see the percentage improvements between one to the next from before and after. So at the bottom of the screen, you see that aggregate score, which shows you the previous process and the re-engineered process. And then a scale on the right-hand side that takes you through 100 to 0, and 0 being most desirable, and where we want to move as many of our products as possible to decrease that impact of the product. Another example of a process that we worked on is 1-aminobenzotriazole. So before, this process was a 4-step process, and it included a hazardous reaction step that we had to use hydrogenation. Even though hydrogenation is a standard procedure to use in any organic synthesis, it introduced risks which we'd like to eliminate. It increases safety, and it decreases the unintended environmental impact that could potentially be there. Once again, our scientists collaborated with various experts and reviewed current literature and came up with a plan to use benzotriazole as the starting material and implemented a single-step amination reaction with benzotriazole. They were able then to scale that reaction up successfully and improve the yield by 30% while eliminating the need for additional heating in the reaction and reducing solvent usage by more than 40%. And so you can see where this hits on some of the principles. You see accident prevention, significant improvement there by eliminating that hydrogenation step. And this is, I think, where we really want to be able to go, is to give you, our customers, more information about these steps taken forward and start to drill down and increase transparency around these products. I'll now take you to the 12 principles aligned category. And here, these are products that have one or more characteristics of the 12 principles. In this left-hand waterfall, you see a comparison of CPME and THF. There's been a lot of information about solvent switches. There are guides put out by the ACS Green Chemistry Institute by a bunch of organizations about helping people to make different choices in their solvent usage. And here's just an example of some of the benefits that could potentially be had by using CPME instead of THF in this large-scale example. So you see a significant waste reduction, really dependent upon the fact of being able to recover solvent in the process. And then secondarily, a carbon footprint benefit. So from a sustainability perspective, this is helping to reduce scope 3 emissions through the need of incineration. So you have to get rid of that waste somehow. So by moving over to the CO2 category, you can reduce the amount of waste that you need to incinerate, decreasing your carbon footprint for these types of products. Another thing that we continue to look at is how do we bring more of these solvents to our customers. So looking at bio-based NMP and DMF replacements, we're really excited about the potential there just based on what's happening with REACH and the need to find something that's going to make a meaningful switch for customers, as well as other bio-based solutions for acetic acid, isobutanol, and paraxylene. Another product that we are in the process of introducing, and a really great collaboration, is with UCSB and the Lipschitz lab about bringing these kits into play where you can do reactions in water. You just have to add the substrate, and there are all of these different reactions that can take place. You see that list there. These are really potentially game-changing products that are introduced to the market to help decrease the impact of research. I mentioned that need for transparency and information. We are in the final stages of beginning to implement updates to our product detail pages to give people information about the green alternative characteristics of these products. So you can see an outline on the screen that highlights the product category that it's in, that being a re-engineered, a 12 principles aligned, or an enabling product. A dozen score, which means that we've gone in and re-engineered that. We covered that with the beta amylase example. 3 main drivers of greenness. One of the important things here is to give you clarity and transparency into what actually is improving. And so you see, be that principles 1, 6, and 8, or whatever mix that is, you'll see those on the screen. And then most importantly, a link to a third-party published paper on why it's considered greener. I think this is really the most important piece, is the fact that it's not just Sigma-Aldrich saying it's greener. There's published research that gives you another point of view about why this is in fact a greener alternative. And then finally, links to other products within that greener alternatives category to increase navigability and to link you to more solutions within the Sigma-Aldrich product portfolio. We've also re-implemented a new homepage for green chemistry to create really a hub of information for our customers. So here you can find the latest news and information, as well as the products that we offer, and more information around how we have put this program together. What do the 3 categories mean? How do you dive into more detail around the dozen campaign so you can learn a bit more? And then I think, once again, it's engaging our customers and you scientists. How do you know what's happening and what's going on? And we kind of see this as you don't know what's happening unless you do know what's happening. And that means, what are you using in your labs? Enterprise level, what are all of the products coming into campus? And so we are really beginning to increase engagement with our accounts around sustainability opportunity dashboards, really outlining what we offer, what we're selling into those accounts, and then potential opportunities to make switches or really quantify the opportunities for improvement at institutions. I mean, I think this is exactly what we would kind of see and think about, and what we're trying to really help. So that idea that my chemistry works, why change it? That's one of the things that we hear most frequently. And so that is one thing that we really try to think about when we talk about education advocacy and changing the cycle earlier on. The real need to be thinking about this in terms of when you're learning this in your formative years in the labs at a university is really imperative to, we think, kind of climbing the mountain and getting over the hump to make green chemistry something that is just the standard. It's no longer kind of its own special thing, but it's going to be everyday chemistry at one point. And so to do that, we're actually have begun a partnership with Beyond Benign to think about how do you change the dynamic on green chemistry education and begin to get universities resources to be able to change the chemistry and the curriculum that they're teaching at their institutions. So right now we are in the pilot phase of working with a university in Texas on the implementation of this. We're hopeful that this starts to go live in the spring semester of 2016, and we'll have results at the end of that semester to better understand implementation and the reaction to students if they're uptaking this, if they get it. We think that there is certainly an appetite. What we hear from millennials is we want more of this and we want to do it ourselves. And so really figuring out how do we get them that information, but also work with universities for the implementation of this, because just like everyone else, they're trying to figure out how do they serve the needs of their students, meet the education demands that are upon them, but also prepare them for the future. And I think that future is going to look a lot different than maybe it looks right now.
So why are there so many companies in the chemical industry not getting more into green chemistry? Or is at least that how it seems? Or in your opinion, is that how it really is? Maybe we'll throw that to you first, David.
I think companies are moving in that direction. Certainly universities and colleges are probably moving a little slower in some ways, but we'll be sending them students, I think, that have some rudimentary understanding of green chemistry. And, we'll have to see how that goes in the interviews when people start to get into industry. Jeff, you want to comment?
Yeah, so I think from an industry perspective, I think there are companies who are starting to move on this, but I think one of the things that holds it back is it really becomes a chicken and egg problem. Is the market there, and are we going to see returns? And we really need organizations to kind of step up, put a flag in the ground, and say, we're going to get behind this, even though it's a nascent industry from a scale perspective. But clearly, if you look at where things are headed, I think what you look at downstream demand from customers, it is natural, it is organic, it is environmentally friendly, and that means we're going to need to work back through the chain, and that's where it's going to become incumbent for industry to be able to provide solutions that meet the requirements of these downstream consumers. I think it's just tough right now because the market demand maybe isn't as big as companies would like to see the returns that they would like currently.
Thanks. Going back to the returns you were just speaking at, Carnine asks, have you found with Sigma-Aldrich that the products produced using these methods tend to be a little bit more expensive than the old way?
Yeah, no, it's a great question. And so in certain cases, the costs go up. Sometimes they go a little bit down. So if you look at that beta amylase example, we were able to reduce the amount of sweet potatoes we used. Unfortunately, sweet potatoes aren't an expensive main ingredient, so it's not like we're reaping these huge savings. But I think what we have always aimed to do is how do we look at price parity and really trying to make sure that there is not an excessive price premium to go green. Sometimes there is going to be one because there's more R&D work required, but on the whole, what we're really trying to aim for is a neutral cost impact.
I'd step in there too for a moment and putting on a safety hat instead of a green hat for a minute here and think about companies that and universities that have to think about the cost of doing business. If that goes up a little bit in order to make a safer environment for their employees and for the environment, certainly there's a PR advantage to that we can't ignore. But if you have one catastrophic event, that's going to cost a lot of money to recover from. This is always the calculus of risk-benefit analysis, and from a safety perspective, it's always easy for safety folks to say, it might cost you a little bit more to be safe for some aspects of this, but considering the lawsuits or the real cost of responding to a major incident, this would be money well spent.
And I think David makes a great point there. And one of the conversations that we're also having, especially with academic institutions, is really around the total cost of ownership. So while the initial product may be more expensive to purchase, if you look at waste disposal costs and the safety aspects that David mentioned, that's where you actually have significant savings and are able to decrease whatever the overall investment is.
Going on a little bit of that, we have Megan writing in from California who brings up water usage, which of course is on a lot of people's minds out there. Do you think that a lot of people are now focusing more on using less water in their process?
As an academic chemist, my sense of this, and this probably bleeds over into industry a little bit too, is that if one of the primary sources of water is simply to be cooling some process, which I gather is a fair heavy use of water in industry, there are other ways to cool reactions. You can recycle the water instead of do single use. So I think this is an area where progress can be made in some cases pretty simply, I would think.
And Beverly was wondering about when to start to bring in the green chemistry education. You mentioned working with colleges, but is there any efforts being made to get down to like the even before that, back to that, like down to the high school level?
There are definitely programs that are happening now that go down into that level. I think the challenge that you face is one of numbers, and the math gets a little more difficult to get that curriculum down into all of those high schools who are implementing that. Where if you take it one step further and where people are digging in a bit deeper into like the core aspects of chemistry, that's where we probably say makes the most sense for implementation. The earlier the better, that's always the case, but I think if we're looking at where we could probably make the most impact with limited resources, it probably is at that introductory chemistry level and then building from there.
I'll chime in here too that Jeffrey mentioned that their Sigma-Aldrich is collaborating with Beyond Benign, and if you go to the Beyond Benign website, you'll see that they really have a K through 12 and college components to what they're trying to do to promote green chemistry at all levels.
Oh, perfect. You actually may be heading me off of my next question. Let's say I have a lab and I want to start instituting either to make it safer or to get more green chemistry principles involved. Where's a good place for me to start?
Yeah, I mean, I think if you look at the ACS Green Chemistry Institute has a really great and robust set of resources and then also kind of a web or network of organizations. So it's a really good place to start. And there's also organizations within GC3 that, once again, have these kind of education networks and informational networks that are really rich sources of information.
Moving back to the industry side, Edward had a question relating to the concept of value associated with a green product. So would you think that there, from the consumer point of view, is more value placed on a product or that can be added to a product when they know it is made more ecologically friendly?
If you look at studies today, you can absolutely see that there is, for consumers, a green premium, and customers are willing to pay, depending upon the category, a nominal amount more than what they might pay for a traditional product because they feel like there is less of a risk or impact that they may face. And I think this is really where transparency becomes important, because if you are feeding information to that next stage of the value chain, that's what's going to enable these value propositions to be extended to customers. And so being able to give them information then perpetuates or gives them the next set of information that they would need to provide to consumers about why that product is indeed a better option than another product.
So I think it's safe to say that we all are interested in green chemistry and the benefits of green chemistry, and probably most of the people in our audience today are also interested in that. But how do you talk the chemist who might not be on their radar, they're more just concerned with the process they have and getting it right, to come around to green chemistry?
I think part of the argument is that this is the direction that chemistry has to move in the future, and you might as well get on board sooner rather than later. We would certainly like the chemical industry to be a lot more benign. If we go back far enough, we can see certainly times when it wasn't, before there were national regulations, about pollution and whatnot, that really left a different earth behind than what most of the millennial generation has ever known about. I think this is the direction we're moving. The costs will, like with many other things, costs eventually come into alignment better with what you'd like as R&D proceeds. It's kind of a cheap phrase, but it's kind of the right thing to do. I think some chemists would say, the bottom line is what's going to drive industry, and as soon as green becomes cheaper, then it'll become more popular. That's certainly true, but I think, as Jeffrey has pointed out, people are willing to pay a little bit more to try to do the right thing. So this is going to be an ongoing process, but some people will remain to be convinced. I don't doubt that.
What we try to do is find exemplars of green chemistry who are really out in front of this issue, who are recognized and respected voices in this space, and then try to pull people along in that vein. Unfortunately, we're pulling, and it's not like people are coming freely. That's starting to change more, but I think more often than not, it goes back to that pull question of the things holding back, and if the chemistry works, why change it? Giving people meaningful reasons why that change is needed, I think, is also part of the imperative of getting people to move to a more benign future.
Now, this one might be a little bit off topic, but we've had a few people ask this questions. If there's, including Thomas, if there's any examples of corporations or other places funding graduate students on their studies of green chemistry.
So that's not currently something that we do. I think we look at this from a structural and systems viewpoint of really how do we support broad application rather than more specific focus through an individual scholarship. So we're looking at a systems approach, not that the individual user is a bad thing, but if we want to see wholesale change, how do we do that on a broad scale? And we work through just a different channel for that.
And actually, just after I asked this question, it was brought to my attention that the ACS Green Chemistry Institute hosts a scholarship based on that similar thing. So further information could probably be found there. And I think that about wraps us up for today. Jeffrey and Dave, do you have any final thoughts you'd like to share? Perhaps maybe we'll start with you, Dave.
I feel like I wear two hats at different times, both as a chemical hygiene officer and someone who thinks a lot about safety, and then as a chemist who cares a lot about the environment. And I see the connections between these now. And I just, in my teaching, and I think I'm sensing growing movement across the country, certainly for much more safety being embedded in the chemistry curriculum. I think green chemistry is getting in there. The new American Chemical Society, CPT, the Committee on Professional Training, is recognizing that these need to be features of any undergraduate who gets trained and educated in chemistry these days. So I think the momentum is building for all of this. The graduates that can talk about safe and green chemistry in an interview with the right company will be doing themselves a big favor to have some of that jargon down and recognize that they want to become part of a company who's interested in these features.
Perfect. And Jeffrey, do you have anything that you'd like to share?
I think building off of what David said, we see the need for more implementers, more adopters of green chemistry. And I think the more voices and the louder that call comes for this type of approach to chemistry, you're going to start to see that sea change happen. And I think if you look at resource constraints, there's a great question about water usage. There are a lot of challenges that we're going to face in the not too distant future. And so it's going to be really imperative for us to get ahead of those things rather than to wait and see what happens when we're behind the 8 ball rather than in front of it.
Thank you for watching this presentation. ACS Webinars is provided as a service by the American Chemical Society as your professional source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.